Here half. Good morning, Nana. Here suppose half-lives of two radioactive nuclei. Okay, and a T half of two radioactive nuclei. A and B. Suppose given as 10 and 20 minutes. Okay. Initially, they have same number of nuclei. Same number of nuclei. Okay. After 16 minutes, find the ratio of decayed number of nuclei of A and B. ఇది పెద్ద కష్టమేం కాదనుకుంటే ఐ థింక్ యూ కెన్ సాల్వ్ ఇట్. మీరే చేయగలుగుతారు దీన్ని.
Yes, sir.
ఓకే. సో దీనికి ఏముంది నాన్న, ఇప్పుడు మన డికేడ్ అంటే వీ హ్యావ్ టు ఫైండ్ అవుట్ ఎన్ ఆర్ ఎన్ నాట్ మైనస్ ఎన్.
N naught minus n.
Right, we have to find out n naught minus n. Okay, నాన్న చేసేస్తానంటారా?
Yes, sir. చేయొచ్చు సార్, ఈజీనే.
అదే నేను అంటాను. అంటే ఎన్ఏ ఎన్బి క్యాలిక్యులేట్ చేస్తే అయిపోతుంది. 60 minutes మీన్స్ ఫర్ ద ఫస్ట్ 6 times కదా.
ఎస్ సార్.
రైట్. T is equals to 6 times to T half of A and 3 times to T half of B. ఈ షార్ట్ కట్ వాడేచ్చు కదా స్ట్రైట్ అవే.
2 power n.
Right, n naught by 2 power 6 and nb is equals to, you can write n naught by 2 cube. So what he is asking, n naught minus na by n naught minus nb. Am I right?
Yes, sir.
So you will get 1 minus 1 by 2 power 6 by 1 minus 1 by 2 power 3. If I cancel n naught, and approximately you can say the answer. What is the ratio? 2 power 6 and how much? Nana?
9/8.
9/8 వస్తుందా after cancelling everything?
ఎందుకని ఈ సమ్ ముందర చేసినట్టున్నాం సార్.
Sir, we have done this
చేశాను
same
ఇది.
problem, sir.
అవును సార్, ఈ సమ్ చేశాను.
ఓహో, అచ్చా, సేమ్ ప్రాబ్లం చేశాను అయితే. ఓకే, రైట్. అంటే మళ్ళీ రిపీట్ చేశాను అనమాట. అంటే ఏ అండ్ బి అనేది సేమ్ చెప్పుకున్నట్టున్నాను 2019లో ఇచ్చాడు అనేది. ఓకే, సరే. ఇంకా నెక్స్ట్ ఇంకేదన్నా మోడల్ అంటే లైక్ ఎమిషన్ ఆఫ్ ఆల్ఫా, ఎమిషన్ ఆఫ్ బీటా అలా కూడా చెప్పచ్చు. అంటే లైక్ దిస్ అనదర్ మోడల్ హియర్. సపోజ్ మీన్ లైఫ్ ఫార్ములా ఐడియా ఉంది కదా నాన్న?
ఎస్ సార్.
The mean life of what he is saying.
సార్ ఏదో డిస్టర్బెన్స్ వస్తుంది సార్.
నాట్ ఫ్రమ్ మీ నాన్న, అది ఇంకెవరో ఓపెన్ చేశారు అది. ఓకే, రైట్. The mean lives of a radioactive substance or 1620 and 405 years. ఓకే, ఎప్పుడు ఒకే సబ్స్టెన్స్ కి 2 మీన్ లైఫ్స్ ఏంటి సార్ అని అడిగితే 1620 years for alpha emission, okay, and 6405 for beta emission. Okay, find the time taken for decay of time taken for the decay of 3/4 of sample. Okay, 3/4 of sample means substance, 3/4 of the substance. ఎప్పుడు ఇది మనం క్యాలిక్యులేట్ చేస్తుంది? ఫైండ్ ద డికే టైం when it emits alpha and beta simultaneously. Try to understand the question properly, Nana. When it is the substance emits only alpha rays, its mean life is 1620. Only beta rays 405. If emits alpha and beta simultaneously to decay, what is the time taken to decay to 3/4 of the original substance? Ante 3/4 of n0. So first question you understood, Nana?
Yes,
sir.
ఇలా ఫర్ ఎగ్జాంపుల్ ఆల్ఫా ఎమిషన్ బీటా ఎమిషన్ అంటే కాస్త కొత్తగా ఉంది మనకి మోడల్. హౌ టు సాల్వ్ దిస్ టైప్ ఆఫ్ మోడల్? దీన్ని ఎలా
సార్ ఇక్కడ
చేయాలి?
నాకు ఒక డౌట్ వచ్చింది సార్.
ఎస్, వాట్స్ యువర్ డౌట్?
సార్ అంటే ఇప్పుడు కొన్ని న్యూక్లియా ఏమో ఆల్ఫా, కొన్ని న్యూక్లియా ఏమో బీటా, అలా ఎమిషన్ ఉంటుందా?
అనే ఉండదు నాన్న. ఓకే, ఏదైనా ఒక సబ్స్టెన్స్ తీసుకున్నప్పుడు టు అటైన్ ద స్టెబిలిటీ ఇట్ మే ఎమిట్ ద ఆల్ఫా రేస్, ఇట్ మే ఎమిట్ ద బీటా రేస్. వాడు ఏం చేస్తున్నాడు? ఎట్ ద టైమ్ ఆఫ్ ఎమిటింగ్ ద ఆల్ఫా రేస్ ఓన్లీ వాడు ఒక మీన్ లైఫ్ క్యాలిక్యులేట్ చేసుకున్నాడు. While it is emitting the beta rays, what would be the mean life he calculated for the same substance? And like for example, uranium 238. Okay, at the time of emitting the alpha rays, what would be the mean life? Okay, అలా తీసుకొని ఇప్పుడు ఆల్ఫా అండ్ బీటా అజ్యూమ్ చేస్తే సైమల్టేనియస్లీ ఇట్ ఈస్ అజ్యూమింగ్ దట్ ఇట్ ఎమిట్స్ ఆల్ఫా అండ్ బీటా సైమల్టేనియస్లీ, వాట్ వుడ్ బి ద mean life or t half? If you are able to calculate, then you can calculate the time taken to reduce to 3/4 of the substance.
Sir, means can we take average, sir, of both the mean lives and take that as
average mean
average of alpha emission and beta emission of the mean lives of
okay.
and take that as t mean for the total when it emits alpha and beta.
1620 ఏమో కదా సార్ రెండిటికి కలిపి 1620 అనుకుంటా సార్.
1620 ఓన్లీ ఫర్ ఆల్ఫా కదా నాన్న?
అంటే సైమల్టేనియస్ గా అవుతుంది కదా సార్.
సైమల్టేనియస్ గా అవుతున్నప్పుడు హియర్ వీ హ్యావ్ టు టేక్ ఇవేంటివి నాన్న? మీన్ లైఫ్ అంటే 1/λA is equals to 1620, correct?
Correct.
And 1/λB is equals to 405. Mean life means 1/λ. Lambda is a decay constant కదా నాన్న?
నాకు
Yes,
ఒక
are you
ఐడియా
saying
వచ్చింది
anything here?
సార్. అంటే ఇప్పుడు ఫస్ట్ మనం కొన్ని న్యూక్లియై ఏమో సార్ వాయిస్
we are finding some lag in your voice, Nana. Okay. Then here, Charitesh and Aryan Kumar, what you said, both not 1620, not 405, actually. Sure, Nana Mandua. Here, lambda is nothing but decay constant. So lambda A is a decay constant when it emits alpha, and lambda B is the decay constant when it emits beta. When it emits both, then lambda should be equal to, for the alpha emission plus for beta emission, we have to calculate what would be the lambda. Okay, this is the basic concept what I am interested to say. Okay, E model usually you find in mains and advanced type of questions. Akkada adagataniki chance undi nanna. Simultaneously emission. Okay, in that case, simultaneous emission lambda of both alpha and beta I'm getting. Lambda is 1 by 1620 plus 1 by 405. Okay, and this is nothing but I think 405 into 4. Yes, correct. This is 405 into 4. So 1 by 405, if I take common, I will get 1 by 4 plus 1. 4 5s are 20, 4 4s are 16. Correct. So this is equals to 1 by 405 into 5 by 4. Means I am getting, that implies lambda of the simultaneous emission of alpha and beta equals to 5 9s are 5 9s. 1 by 91 into 4. That is equals to 1 by 4 9s are 34. 364. No.
81 into 4. Sir.
81, no? 4, sorry. You are right, Nana. 81 into 4. 5 8s are 5 1s are. Into 4. 324, I think. Now it is correct. Am I right?
Correct, sir.
Right. By this you found lambda, Nana. Okay. Of course, if you find the means basic concept you understood, Nana. Directly we should not take mean and we should not take. Is it correct?
Means sir, they found this practically, sir. This lambda is
Yeah.
equal to lambda plus lambda.
Obviously, Nana. So it is a constant for a given substance now while emitting some certain radiation.
Yes, sir.
It is a constant for me. That
Okay,
constant we have to.
Yes, sir.
Usually they take by the emission of alpha, beta, gamma, everything. They say for an element. Usually this is the of certain element.
Okay,
But here
yes,
he
sir.
says
Understood.
separate for alpha emission how much, separate for beta emission how much. Okay. Then coming to here. Here for the decay of 3/4 means after the decay of 3/4 of substance, we will get what, Nana? N is equals to 3/4 of N naught or something.
3/4 of N naught.
3/4 decay.
1 by 4, sir.
N N is undecayed kada, Nana.
Yes, sir. Sorry.
Which is not disintegrated, radioactive. So we should not do the mistake. So N is equals to N naught minus 3/4 of N naught. This is already decayed. Undecayed is 1/4 of N naught. So we can write here. That implies he is asking the time. Na? So here N is equals to N naught into e power minus lambda t. All these things you can understand. If you take these two cares here. One, here N is whether 3 by 4th of N naught or 1 by 4th of N naught. Number two, what is the lambda? Rest of the things without my explanation you can solve. That implies this is n naught by 4 is equals to n naught into e power minus lambda t. So after cancelling and reciprocating, I will get 4 is equals to e power plus lambda t, and log 4 is equals to lambda t. Log 4 is 2, log 2 equals to lambda is log 2 by lambda. Already I calculated, I think. 1 by, how much is this? I got 324. 324 into t. Is it correct, Nana?
Correct.
Yes, sir.
That implies 324 into 2. 648 into log 2 is approximately 0.7. I don't know how much is this calculation. Approximately, will you tell, Nana, this is? Thank you, Nikhil.
453.6.
Yeah, exactly. Is equals to t approx. What we got? Yeah. In option, he gave 450, Nana. So is it correct?
Correct.
Okay, by taking 0.69. Right. That implies t is equals to given option 450 ES. Okay, this is exact what he said. Okay, ఇప్పుడు this type of model will you solve, Nana? When they give two decay constant for the same material, how to calculate the decay constant?
Yes.
Okay. Like many models are there, Nana. ఇలాంటి చాలా ఉంటాయి మనకి మోడల్స్ దట్ యూ హ్యావ్ టు ప్రాక్టీస్. మరి వెన్ యూ ప్రాక్టీస్ ఆల్ దోస్ థింగ్స్ చేస్తారా? Actually, I
Yes,
plan
sir.
to give this.
Yes, sir.
Coming to here, the concept of what we say for the stability of the nucleus. What I said, Nana, the protons and neutrons they decay like mesons and blah blah blah. So that they try to attain some stability and చెప్పాను previously long back. Okay, how it attains the stability, provided it is not unstable, it is stable. At that time, during those disintegrations inside the nucleus, what Yukawa proposed, like proton neutron reactions, neutron proton reaction, proton proton neutron neutron, remember none of that one? Disintegrates into proton and releases like a pi zero meson.
Pi meson.
Like pi mesons, remember?
Yes, sir.
Right.
Strong
Good.
nuclear force.
Strong, which leads to strong nuclear force. Because of those disintegrations, in the meanwhile, we can find some defect in the mass, Nana. Means practically whatever we measure the mass, that the nucleus won't possess. And what you are saying, we did not follow properly, sir. Yes, what I am saying is, suppose without explaining any theory, if I ask, how you calculate the mass of nucleus, then what do you say? What is there, sir? Suppose if you take a nucleus, it contains Z protons and A minus Z neutrons. Correct, Anana?
Correct.
Suppose there are 2 protons and there are 4 neutrons. Okay. Anukundam. 2 protons and 4 neutrons. Then what is the total mass of nucleus? Means what I say? The mass of proton plus mass of neutron is the mass of nucleus. Is it right?
Yes, sir.
Right.
So mass of proton means number of protons Z. So Z into mass of proton MP plus mass of neutron A minus Z into Mn. Usually we say this. This is the mass of nucleus. Okay. Due to continuous disintegration, what happens if you practically calculate mass of nucleus, measured practically, and without using this equation practically, okay, suppose that is m, mass of nucleus practically is m. These two are not equal, Nana. That's they found. Okay, and that mass is always less than the mass of their constituents. Means here, suppose if you take it as some m dash, better I write here. Suppose if you take it as m dash, what you measured here, yeah, m dash is not equal to m, what they found. Okay, means that theoretically what should we get, that practically we are not getting because of the continuous disintegrations. So they found here some mass defect inside the nucleus. That implies here the practical observation is m is less than m dash. This is the practical observation, Anna. That difference between the theoretical mass and the practical mass is the mass defect. Okay, that implies uh, m is less than m dash, means I have to take m dash minus m is called the mass defect, represented with delta m. Okay, this mass defect assumption, what they took here, they found same mass defect in all reactions in organic chemistry also. That's why those reaction, in every reaction we can find some release of energy. Those type of reactions are called as exothermic, I think, if I'm not wrong. Are they exothermic or endothermic, Nana?
Exo.
Exothermic.
If they release the energy, they are called as exothermic. Okay, to combine, suppose they absorb the energy, that is called as endothermic, I think.
Yes, sir.
Yes, sir.
Yeah. Yeah, that means here, there also, I think you found the what is the total mass, means like x plus y results to z plus some energy, if you write like this. And by the combination of this x plus y, we usually calculate the total mass of z and total mass of x, total mass of y, means I'm saying nucleus. Okay. And then here the mass, total mass is not equal to that. There is finding out some mass defect between the parent nucleus and the daughter nucleus. Okay. So here that difference is converted into energy. This usually we use in chemistry, Nana, reactions. Okay. That gave the strong support to this mass defect even inside the nucleus. Okay. So we have to accept this one. Mass defect is there inside the nucleus. That mass defect numericals are here very disgusting models. All those are delta m is equals to here m dash zmp plus a minus z into mn minus capital M. Here finding out, they give MP value like 1.0004, Mn is equal, so they give 1.000567 or 484, like this they give. We have to do the multiplication, again subtraction, again converting into binding energy multiplied with 931.5 MeV. Look at, we have to take long, lengthy multiplications and time killing problems, Nana. That's why really I won't like such type of models, but we have to do for exams, practical, for objective exams. So actually it may or may not be painful to the students. Some students like such type of calculations. So I think it is really interesting for you, maybe. Okay, this is the mass defect, Nana, what he said. And you remember it as mass defect. And keep in mind, it is measured in AMU, not in kgs. So when you come to numericals, delta M here is measured in atomic mass units. Why? Because mass of proton, mass of neutron, very small. That's why usually we measure in atomic mass units. Okay. That difference in mass means loss of mass here. Okay. According to science, we have to accept that there should not be any loss, there should not be any gain. That should be transformed into some other form. Here, Einstein proposed one equation. Whatever the mass, here we are finding out the defect is not destroyed practically, that is converted into energy. For that conversion, he gave the equation. All of you know the famous equation mc square. Okay, that energy, whatever you are getting because of annihilation of this mass, delta M, is called as binding energy. So next point, what he says, the binding energy here, which is represented with BE, binding energy, is the equivalent mass for mass defect, delta M into C square. It is the equivalent mass of, equivalent energy of equivalent, energy of mass defect. Okay. Where since delta M is in atomic mass units, the binding energy usually will be very less, and it is measured in mega electron volts, Nana. So when you come to numericals, it is measured
Sir, in
in
mains and other
M.
exams, they'll give, sir, this question.
Yeah, that's what I'm saying. Suppose few questions are given easy and few other questions are given tough. Okay. At the easy questions, you are saving the time now.
Yes, sir.
That time they are
Okay.
obviously.
Yes, sir.
Where they kill, like giving these type of questions or giving some analytical questions.
Okay, sir.
So surely you find.
Okay, sir.
Okay.
Yes, sir.
Even in advance also, like paragraphs, you can find these type of questions.
Okay, sir.
These what we say banda questions. Okay. Right. Then come to here, Nana. Here again in these lengthy questions, not lengthy, here painful questions. Again, we need some shortcuts, Nana. Means what, sir? If I find a mass defect in AMU without using this formula, how to find the binding energy? That conversion you see here. 1 AMU, you can use it like a biscuit model, Anna. 1 AMU, suppose if you are able to find out what is the equivalent binding energy, is equal to how much energy if you calculate, that you will get 931.5 MeV, Nana, using the formula E is equals to mc square. Okay, you can check there. 1 AMU is 1.67 into 10 to the power of minus 27 kg. C square is 3 into 10 power 8 whole square. If you do like this, you will get in joules, but we require the energy in MeV. So divided by 1.6 into 10 to the power of minus 13, if you take, then you will get the energy in MeV. Okay. This one, what I am saying, 931.5, you will get it. If you have the calculator, you can check whether my value is correct or wrong. Okay, this is the equivalent energy for 1 MeV. 1 AMU. Okay, suppose if you get the mass defect 0.048, Then we use this calculation, Anna. 1 AMU 931.5, 0.048 AMU, how much? Means into 931.5. Now you understood the concept, Nana?
Yes, sir.
So delta M in problems we calculate. After getting the delta M in AMU, directly we multiply with 931.5. Good. Right. Thank you. So here we are coming to that one. So directly we write here. What's that implies binding energy is equals to whatever you calculate the delta M in AMU into 931.5. If you take this, you will get in MeV, mega electron volts. So when we come to numericals, we use this equation instead of binding energy is equals to mc square. This is a shortcut for our numericals. Instead of this equation, be is equals to delta mc square. Okay, that is just a theory, but when we come to numericals, we never use this equation. Directly we go to that shortcut, delta m into 931.5 MeV. Okay, then you may ask, sir, this energy is required for what purpose, sir? Very simple. We have to keep all the nucleons very close to each other to the distances of Fermis in a closed region. Okay, we require some energy. That energy to bind all the nucleons to the nucleus is called as binding energy. Now you understood, Nana, this theory? This is the energy required to bind all the nucleons.
All the nucleons will get
All the nucleons, keep in mind. So it is, that implies it is the energy to bind all the nucleons, not to escape all the nucleons to the nucleus. Like a closed palm, by closing all the 5 fingers. Okay, it binds everything to the nucleus. So it is the binding energy of all nucleons, means they ask in exam, what is the binding energy per each nucleon? Okay, that implies, what do you say for that? Binding energy per each nucleon?
divided by A.
A or Z?
Means A, sir.
Mr. Mandua, no. Here I am getting some disturbance, Mr. Okay, right. Mr. Mandua, that nuclear force only resulting this mass defect, na? That mass defect only giving the binding energy, na? So this is the another way of explaining how the nucleons are bound to the nucleus. Okay. Now means alternate explanation for the nuclear force. Right. Good. Because of that nuclear force only we are finding out delta M. Then this delta M is for what purpose? For energy. For what purpose? To bind the nucleons. Okay, good. Then here what our Aryan Kumar said, correct. This for a number of nucleons, that implies binding energy per each nucleon. Here is called binding fraction, Nana. Okay, suppose if you represent that binding fraction with the F, then I say F is equals to binding energy per each nucleon, means divided by number of nucleons. Number of nucleons given by mass number, so divided by A. This is the binding fraction. Okay, So this is one more formula we use when we come to numericals to find out the binding fraction. Okay, binding energy for all the nucleons, mass defect here, and we never use this equation when we come to numericals. And here, this is the binding fraction. These are the three equations we use in numericals now. Okay, this binding fraction is taken on y-axis like this. Oh, sorry, like this. And this is the mass number, what we are taking, number of nucleons on x-axis. This is not binding energy, Nana, keep in mind, binding fraction. Okay, so binding fraction for each nucleon, yes, and this is the mass number. Okay, mass number won't start from 0. Do you find any element with mass number 0, Nana?
No, sir.
Mass number 1 means that we consider as a single proton. That's why even we won't consider that as here to find out the binding fraction for single proton. So to find out the binding fraction here, A value must be greater than 1, means at least 2. That's why we start the A value from 2 nano. Okay, not from 0. That's why here this is not start from origin, this will start from 2. This is what I'm saying. Okay, means we calculate the binding fraction from deuteron. This is H12. So here note I am writing the binding fraction is calculated from the element deuteron H12. This is nucleus of deuterium, Nana, deuteron. Now you understood, Nana? Hydrogen, why we are not taking? Why? Because there is only one proton inside. For one proton, this is binding energy and a binding fraction for one nucleus, one nucleon, how much? And is really foolishness. Okay. So we calculate here from deuteron. This is they found for deuteron nearly 1.1 MeV, Nana. So graph starts from 1.1 MeV from here. Okay, and this binding fraction increases element to element, so that it is saying that all these elements are strong. Why? Because binding fraction is increasing with the increasing of atomic number, sorry, mass number, and yet one point it is becoming maximum. Further, gradually it decreases like this, not rapidly, gradually decreases. And that binding fraction we stop calculating from uranium series, that is from radioactive series. Okay, so in this graph, what are the important points, sir? What is the minimum binding fraction, and that is for which element? First point is over, already I told here. This is binding fraction. Okay, this is the conclusions from the binding fraction from the graph of binding fraction and mass number.
Sir, one doubt, sir.
Okay, yes.
Sir, in this graph, means if suppose we are going further, if we increase A like from 2, 3, 4 like that, F will be like
Yeah.
B by 2, 3, 4 like that, no, sir.
Yeah, obviously.
Means then it should decrease, no, sir. Binding fraction.
Binding energy also increases now.
Oh, okay, sir. Okay, sir. Okay, sir.
Yeah, binding energy increases, mass number increases, the fraction increases. That's what it means. Initially, they are not linear.
Okay, sir. Understood.
That's why it is not a straight line. Okay, I took it as like a curved line.
Okay, sir.
Right. So here, this is the maximum binding fraction that they found for iron. Iron, I think Fe56 mass number.
Yes, sir.
Okay. Further, it decreases. Okay, but gradually, not here. You observe 2 to 56 very sharply increases. But here 56 to almost uranium 235 means 56 to 235 very slowly decreasing. And I think you understood here strong nuclear force is supporting, there weak nuclear force is supporting. Further, Coulomb repulsive force is dominating. I think you understood in the graph. Correct, Anana?
Correct.
Right, good. Here. So conclusions are, number one, the binding fraction F is minimum for deuterium. Since binding fraction is very less, it is very easy to fuse, combine. That's what I'm saying. Okay, that implies they can be fused. It results to nuclear fusion, Anna. Keep in mind, buffer point. Okay, and number two, here F is maximum. Okay, this is 8.6 MeV. F is maximum for iron 56. Okay, this is iron. That implies it cannot be splitted, means fissioned, or okay, better I write. Idedo grammatical error kanapadutundi. It cannot be used for fission or fusion. Fission means splitting the nucleus, Nana. Fusion means combining the nucleus. Since F is maximum value, they are not interested to combine, they are not interested to split. And not so easy. Yes, right. And number three, okay, F is less, not maximum, not minimum. Here at iron 256, Nana, 235, sorry. This value is nearly 7.6 MeV, Nana. Even though number of nuclei around 235, you are getting just 7.6 means here F is less, okay, for radioactive nuclei. And they are unstable. Originally, they are unstable. That's why they are used. It can be who the unstable nucleus. It can be okay used for fission. Okay. So how you split the radioactive unstable nucleus into number of different elements, or how to fuse these lighter nuclei to combine. Okay, how to combine. We will discuss in the next class, Nana. Okay, do you have any doubts from this graph?
No, sir.
No, right. So shall I stop it now? Okay.